Welcome to the full video lecture on inference for one sample. The content covered in this video can be found in the Lock 5 textbook, Chapter 6, Sections 1, 2, and 5. Before we begin, I would like for you to review the general form of a confidence interval and the general form of a test statistic. You've seen these in previous lessons. The general form of a confidence interval and the general form of a test statistic will be the same for all of the procedures covered in this lesson as well. These are the 4 learning objectives that we're going to be covering in this lesson. We're going to be covering each learning objective for one sample proportion, one sample mean, and paired means. This is the outline of this video lecture. As you can see, there are 12 different topics that we need to cover. These videos do often get long, so I recommend that you do not watch this video in its entirety. You should stop and take breaks. A natural place to take breaks is either between each learning objective or between each of these subtopics. So for example, after we cover one sample proportion, you may want to go back and review section 6.1 of the textbook or do some section 6.1 questions in Wiley+. Let's start now by looking at one sample proportion. Last week, we learned that the central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. This includes one sample proportion, one sample mean, and paired means that we'll look at this week. Here are 2 bootstrap distribution plots that you can compare. On the left, we have a sample size of 10 and a sample proportion of 0.500. On the right, again we have a sample proportion of 0.500, but now we have a sample size of 100. Comparing these 2 distributions, we can see that the one on the right resembles a normal distribution, while the one on the left has rather large gaps between each of the possible counts. A question that you may be asking now is, at what point does the distribution become close enough to being approximately normal that we can use the z distribution? These are the general guidelines that we're going to be following in this course. This is sometimes referred to as the rule of sample proportions. According to the rule of sample proportions, if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we use the z distribution. Note that n times p is the number of successes and n times 1 minus p is the number of failures. If n times p is less than 10 or if n times 1 minus p is less than 10, we use a binomial distribution. In Minitab Express, if we want to use the z distribution, this is known as the normal approximation method. If we want to use a binomial distribution, this is known as the exact method. Note that in Minitab Express, the default is to use the exact method. We need to check this assumption ourselves by hand and then tell Minitab Express if we want to use the normal approximation method or the default exact method. Minitab Express does not check this assumption for you. Our second learning objective was to construct a confidence interval using the appropriate common distribution using formulas in Minitab Express. We're only going to look at the formulas that are used with the normal approximation method. For the exact method, a binomial distribution is used. You learned about these last week. There aren't any formulas associated with this, but you can do this in Minitab Express by using the default exact method. Let's look at the formulas that are used with the normal approximation method now. The general form is the same that we've seen in previous weeks. The sample statistic plus or minus the multiplier times the standard error. In this case, the sample statistic is p hat, our observed sample proportion. The multiplier for the normal approximation method is going to come from the z distribution. Last week, you learned how to construct a z distribution in Minitab Express and in StatKey to find multipliers. This is in your online notes. These are the most frequently used multipliers. Most often we'll have a 95% confidence interval, which will have a multiplier of 1.960. Earlier in the course, we often rounded this to 2, but from here on out, I'd like you to use the more precise number of 1.960. The standard error for one sample proportion is equal to the square root of p hat times 1 minus p hat divided by n. We can take these values now and plug them into that general form of a confidence interval. This gives us the formula for constructing a confidence interval for p using the normal approximation method. Again, this is p hat, the sample statistic, plus or minus the z multiplier from the z distribution, times the standard error. Let's look at one example. In a random sample of 100 students enrolled in an advanced level statistics course, 79 were statistics majors. Construct a 95% confidence interval to estimate the proportion of all students enrolled in advanced level statistics courses who are statistics majors. From this scenario, we know that n times p, or the number of successes, is equal to 79. N times 1 minus p, or the number of failures, would be 100 minus 79, which is 21. Both of these values are greater than or equal to 10, so we can use the normal approximation method. Here's our formula. P hat is going to be 79 over 100. This is our sample proportion, which equals 0.79. The z multiplier we can get from a z distribution. We need the z-scores that separate the middle 95% from the outer 5%. In the table we saw earlier that the z multiplier for a 95% confidence interval is 1.960. Once we have these values, I like to begin by computing the standard error. The standard error is in the parentheses here, square root of p hat times 1 minus p hat divided by n. Plugging in our value of p hat and our sample size of 100, we have a standard error of 0.041. Now we have all the values that we need to construct our confidence interval. P hat of 0.79 plus or minus our z multiplier of 1.960 times the standard error that we just computed. We have a margin of error of 0.080 and a 95% confidence interval of 0.71 to 0.87. To interpret this, I would say that I am 95% confident that the proportion of all students in advanced level statistics courses who are statistics majors is between 0.71 and 0.87. Now I want to go to Minitab Express to show you how you could do this in Minitab Express much quicker. When we go to Minitab Express, there's a few values that we'll need to know. You might want to take a moment now to write down the number of successes, which is our x value. This equals 79. Our sample size, or n, of 100. And our confidence level, which was 95%. Remember, when we go into Minitab Express, we'll also need to tell it to use the normal approximation method. Let's go to Minitab Express now. I'll go to Statistics, One Sample Inference, Proportion. I have summarized data. Number of events is the number of successes, in this case 79. The number of trials was the total sample size of 100. We can see down below there's a box to perform a hypothesis test. At this point, we're not performing a hypothesis test, but we will do that shortly. Here we just want the confidence interval. Under options, we are constructing a 95% confidence interval, which is the default. We will need to change the method. The default method in Minitab Express is the exact method, which uses the binomial distribution. But recall that n times p and n times 1 minus p were both at least 10, so we use the normal approximation method. Here, our 95% confidence interval for p is 0.710169 to 0.869831. On your lab assignment and quiz this week, I recommend using Minitab Express whenever possible. It tends to be much quicker than doing the calculations out by hand. Let's go back to our PowerPoint. Our next learning objective is to determine the necessary sample size for constructing a confidence interval. This formula is from your notes and the textbook. This is the formula that we'll use to find the sample size necessary for estimating a population proportion with a given margin of error. In this formula, n is going to be the necessary estimated sample size. Z is the Z multiplier. This is going to vary depending on your level of confidence. Typically, we'll be looking for a 95% confidence interval, so this will be 1.960 most of the time. M is the margin of error. So when we're determining necessary sample size, we need to know what margin of error it is that we're trying to obtain. For example, I want a margin of error of plus or minus 0.1. Or I might want a margin of error of plus or minus 0.02. This value will be given to you in this scenario. The P with the tilde is an estimated value of the proportion. You may be given this value in the scenario. If not, if we have no preconceived idea of the value of the population proportion, then we use 0.50 because it's the most conservative and will give us the largest sample size calculation. So if you're given an estimated value of the population proportion, use that value in this formula. Only use 0.50 if you don't have any idea what the population proportion could be. Let's look at one example of this. We want to construct a 95% confidence interval for the proportion of all students enrolled in advanced statistics courses who are statistics majors with a margin of error plus or minus 2%. From a previous study, we know that the population proportion should be around 79%. So we're using the data that we collected earlier when we constructed that earlier confidence interval, and we have an estimate of the population proportion, so we'll use that in our formula. The Z multiplier, again, a 95% confidence interval is going to be the most common confidence interval with a Z multiplier of 1.960. We have an estimated value of the population proportion. In this case, we were given a percent, 79%. Remember that you need to change this to a proportion. A proportion must be between 0 and 1.00. So in this case, this translates to 0.79. Our margin of error was given to be 2%, which we can translate to a proportion of 0.02. We plug these values into our formula, and we find n equals 1,593.304. In this case, we're going to round up. You always want to round up to be more conservative when estimating your necessary sample size, so we would obtain a minimum sample size of 1,594. Let's look at one more example. We want to construct a 95% confidence interval for the proportion of all Penn State students who are registered to vote with a margin of error of plus or minus 5%. Note that in this case, we're not given an estimate of the population proportion, so we're going to estimate that using 0.50. For a Z multiplier, again, we want a 95% confidence interval, so that's going to be a Z multiplier of 1.960. We don't have an estimate of the population proportion, so we're using the conservative estimate of 0.5. And we're given a margin of error of 5%, which as a proportion translates to 0.05. We plug these values into our formula, and we find a minimum necessary sample size of 384.16, but we always round up. So we would want to obtain a minimum sample size of 385. Finally, we'll move to the last and actually largest learning objective, conducting a hypothesis test. We'll walk through each of these steps in a little more detail now. Step 1, check assumptions and write hypotheses. In terms of checking assumptions, we're going to be looking at the rule of sample proportions again. If n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we use the z-distribution. Note that the value of p that we're going to be plugging into this equation is p from the null hypothesis. If this is true, then we use the normal approximation method. If this is not the case, so if n times p is less than 10 or if n times 1 minus p is less than 10, we use a binomial distribution. Minitab Express will call this the exact method. In terms of writing hypotheses, this is the same that you saw in an earlier lesson when you were first introduced to hypothesis testing. Our null hypothesis is always going to be that p equals some given value. So the p sub o that you see here is the hypothesized population proportion that you're given in your scenario. The alternative hypothesis then is going to depend on your research question, whether you want to know if the proportion is different than that value, greater than that value, or less than that value. Step 2, we calculate the test statistic. In this course, we're just going to be calculating the test statistic for the normal approximation method by hand. This is the formula for a z-test statistic for one sample proportion. P hat is your observed sample proportion. P sub o is the hypothesized population proportion. So this is the number that's in your null hypothesis. And n is your sample size. Note that this is similar to the general form of a test statistic that you've seen before. We have the sample statistic minus the null parameter in the numerator, and in the denominator, we have the standard error. Another thing to note here is that the standard error for hypothesis testing with one sample proportion is slightly different than the formula that we just used when we constructed a confidence interval. When we constructed a confidence interval, the proportion that was used to compute the standard error was the observed sample proportion. Now, the value that's in our standard error formula here is P sub O, the hypothesized population proportion. Step 3, determine the p-value. The area under the z-distribution more extreme than our test statistic in the direction of the alternative hypothesis is our p-value. Again, we'll walk through an example of this here, and you'll see some more examples in the online notes. This is similar to what we saw when we conducted randomization tests. Remember, the p-value was the area on the randomization distribution that was more extreme than our observed test statistic. So in StatKey, we would construct the randomization dot plot, and then the p-value would be the area more extreme than the observed test statistic. It's the same idea here, except now instead of using the randomization distribution, we're using a z-distribution. And instead of using the actual test statistic as the cutoff, we're first converting it to a z-test statistic. In this particular plot, we have a z-distribution. Note the mean of 0 and standard deviation of 1. And we must have had a z-test statistic of 1.55 and a right-tailed alternative hypothesis. So we constructed a z-distribution and we found the area more extreme than our observed z-test statistic, which gives us our p-value, which Minitab Express will also highlight in red. Step 4, make a decision. This is where you are going to reject or fail to reject the null hypothesis. This is based on the p-value that you computed in step 3. If p is less than or equal to alpha, we reject the null hypothesis. Unless stated otherwise, use an alpha level of 0.05. If P is greater than alpha, we fail to reject the null hypothesis. In step 5, state a real-world conclusion. Go back to the original research question and make a meaningful conclusion. Be sure to use the variables and aspects of the population that are given to you in the scenario. Let's look at one example. Here's our research question. Is the proportion of all students who take STAT 200 via World Campus who identify as women greater than 0.50? In a random sample of 45 students, 26 were women. Step 1, we'll check assumptions and write hypotheses. In order to use the normal approximation method, n times p and n times 1 minus p must both be at least 10. In hypothesis testing, the value of p that we're going to be using is the value from the null hypothesis. Here, the hypothesized value is 0.50. Our sample size is n equals 45, and p sub o is 0.50. N times p sub o equals 22.5, and n times 1 minus p sub o also equals 22.5. These are both greater than or equal to 10, so we're going to use the normal approximation method in this example. Next, we write our hypotheses. The hypothesized value is 0.50, and we want to know if the population proportion is greater than this value. So we have a right-tailed test. This is going to be our alternative hypothesis because it contains greater than. Our null hypothesis will be that p equals 0.50. Step 2, calculate the test statistic. Here's our formula for the z-test statistic. P hat is our observed sample proportion. In our sample, 26 out of 45 identified as women, giving us a sample proportion of 0.578. P sub o then will be the value from the null hypothesis. Here, P sub o equals 0.50. N is our sample size of 45. Now that we have all of our values, I usually like to begin by computing the standard error. The standard error is underneath the square root symbol here in the denominator. We plug in our values and get a standard error of 0.075. Now, we find the z-test statistic by taking our observed sample proportion minus the hypothesized proportion divided by the standard error, giving us a z-test statistic of 1.040. Step 3 is to determine our p-value. This is the area under the z-distribution more extreme than our test statistic in the direction of the alternative hypothesis. In order to find our p-value, we're going to have to go to StatKey or Minitab Express to construct a z-distribution to find the area greater than z equals 1.040. Let's go to Minitab Express now. I'm going to go to Statistics, Probability Distribution, Distribution Plot. I want to construct a z-distribution to display a probability. The default is a z-distribution, a normal distribution with a mean of 0 and standard deviation of 1. I have a specified x value. This is our z-test statistic of 1.040, and we have a right-tailed test. Here's our p-value, 0.149170. Now that we have our p-value, we can move on to step 4, make a decision. Our p-value is greater than the standard alpha level of 0.05, so we're going to fail to reject the null hypothesis. In step 5, state a real-world conclusion. We'll go back to that original research question to make a meaningful conclusion. We failed to reject the null hypothesis, so there is not evidence that the proportion of all students who take STAT 200 via World Campus who are women is greater than 0.50. Next, I'm going to take you back to Minitab Express to show you how steps 2 and 3 can be computed together there. On the lab assignments, I strongly encourage you to use Minitab Express when possible to calculate the test statistic and the p-value. You're much less likely to make an error if you're doing these steps in Minitab Express. In Minitab Express, I'll go to Statistics, One Sample, Inference, and Proportion, just like we did earlier when we constructed that confidence interval. We're entering in summarized data. The number of events is the number of successes, so in this case there were 26 women. Number of trials is the sample size, which was 45. We need to tell Minitab Express now that we are conducting a hypothesized test, and the value that we are testing is P sub O of 0.50. Under options, we need to change the alternative hypothesis. This is a right-tailed test. And we need to tell Minitab Express to use the normal approximation method. Here we have a z-test statistic of 1.04 and a p-value of 0.1484. You'll still need to do steps 1, 4, and 5 of the 5-step procedure by hand, but on the lab assignments and quizzes, I recommend that when possible, you use Minitab Express to compute the test statistic and the p-value. If you've not done so already, this is a good time to stop and take a break. What we've covered so far is covered in section 6.1 of the Lock 5 textbook. I recommend going to the online notes now and reviewing the section on inference for one sample proportion, or going to section 6.1 of the textbook to review. You may also want to go into Wiley Plus and answer some of the practice problems or start the homework problems that are tied to Chapter 6, Section 1. After you take a break, come back and we'll start again with one sample mean. We just covered one sample proportion. Now we're going to go through those same 4 learning objectives with one sample mean. We'll start with identifying when the z and t distributions should be used. I have a flowchart to help us with this. There are 3 questions that we'll need to ask. Is the population normally distributed? Is the population standard deviation known? And is the sample size at least 30? The first question you need to ask is the population normally distributed? In this course, this will often be given to you in this scenario. If not, there are tests that we can do using sample data to determine whether or not the population is likely skewed. We're not going to cover those in this course, though. In this scenario, you would be told that the population was normally distributed. When this is the case, the next question we need to ask is the population standard deviation known? If yes, then you're going to use the z-distribution. This is not a test that is required in this course. It is in the online notes, though, as an optional section. You'll see this most frequently in the social sciences, particularly education and psychology, where they work with IQ tests and SAT and ACT tests, where the population is known to be normally distributed, and the test is normed to have a specific population standard deviation. Depending on what field you're in, though, you may or may not come across this. If the population standard deviation is not known, which is going to be most common in this course and in most cases, then you would use a t-distribution. In a minute, we'll look at what a t-distribution is. It's very similar to a z-distribution, but it does take into account the sample size a little bit. If we go back to the beginning, what if the population is not normally distributed? So in this class, if in this scenario, you're not told that the population is normally distributed, or maybe you're told that the population is skewed. The next question you would need to ask is the sample size at least 30? According to the central limit theorem, if the sample size is at least 30, regardless of the shape of the original population, the sampling distribution will be approximately normal. In those cases, we use the t-distribution. If the sample size is less than 30 and the population is not normally distributed, Then you would go back and you would use the bootstrapping and randomization procedures that you learned earlier in the course. In this lesson, what we're focusing on is the t-distribution method. The t-distribution is symmetrical, like the z-distribution. The difference is that it varies depending on degrees of freedom. Degrees of freedom are going to be computed using sample sizes. For the one sample test that we'll see first, the degrees of freedom is equal to the sample size minus 1. Here we have a distribution plot of two different t-distributions. The solid blue line represents a t-distribution with 4 degrees of freedom, while the dotted red line is a t-distribution with 40 degrees of freedom. We can see as the degrees of freedom increases, the shape changes slightly. The center becomes a little bit higher, and the tails become a little bit lower. Here we can compare a t-distribution with 4 degrees of freedom to a normal distribution. We can see with small degrees of freedom, the t-distribution is lower in the center and the tails are a little bit higher. As the degrees of freedom for the t-distribution increases, so here we have 40 degrees of freedom, the t-distribution becomes closer to the normal distribution. So here with 40 degrees of freedom, we can see that the t-distribution is almost right on top of that z-distribution. Let's look now at how we can use the t-distribution to construct a confidence interval for one sample mean. The formula for a confidence interval for one sample mean is going to follow the same general form. The sample statistic now is x bar, our observed sample mean. The multiplier, we're going to be focusing on the t-distribution. It's also possible if the population is normal and the population standard deviation is known that you could use a z multiplier. But for the majority of the tests that you're going to see in this class and in real life, a t multiplier is going to be used. Degrees of freedom for one sample mean are equal to the sample size minus 1. The standard error is computed as s divided by the square root of n. S is the sample standard deviation, and n is the sample size. We put these values together, and we have x bar plus or minus the t multiplier times the standard error. Let's look at one example now. In a representative sample of 70 students, the mean quiz score was 14 with a standard deviation of 2. Construct a 95% confidence interval to estimate the mean quiz score in the population of all students. From this scenario, we're given n equals 70, x bar equals 14, and s equals 2. To find our t multiplier, first we need to compute the degrees of freedom. For one sample mean, degrees of freedom are equal to n minus 1. This gives us 69 degrees of freedom. Now we can go to Stack Here Minitab Express to construct a t-distribution with 69 degrees of freedom to find the multipliers that will be used for a 95% confidence interval. Let's go to Minitab Express now. Here I'm going to construct another probability distribution plot, this time for a t-distribution. We have 69 degrees of freedom, and we want to find the t-scores that separate the middle 95% from the outer 5%. So we have 5% that is split equally between the two tails. Our t multiplier is 1.99495, which we may round to 1.995. Now we have all the values that we need to plug into this formula. Our margin of error is 0.477, and our 95% confidence interval is 13.523 to 14.477. To interpret this confidence interval, I could say that I am 95% confident that in the population of all students, the mean quiz score is between 13.523 and 14.477. Now let's go back to Minitab Express so I can show you how this could be computed there. The information that we'll need to take to Minitab Express is n equals 70, x bar equals 14, and s equals 2. I'll go to statistics, one sample inference, t. Recall, because our sample size is greater than 30, we're using a t distribution here. We have summarized data. Our sample size was n equals 70. The sample mean, x bar, was 14, and the sample standard deviation was 2. Below here, we see we have a box that we could check if we wanted to conduct a hypothesis test. We're not going to be doing that right now. Under options, the default is a 95% confidence interval, which is what we want. We'll click OK. And our 95% confidence interval for the population mean is 13.5231 to 14.4769. On the lab assignments, quizzes, and Wiley Plus, I recommend whenever possible that you use Minitab Express. Our next learning objective is to determine the necessary sample size for constructing a confidence interval. Here's the formula that's going to be used when estimating a sample size for one sample mean. Again, n is the estimated minimum sample size. Z is a Z multiplier for a given confidence level. I know that we're using the T multiplier when we're constructing the confidence interval, but remember that the T multiplier is going to depend on the degrees of freedom, which is directly related to the sample size, which is what we're estimating here. So because we can't plug in a T value because we don't have the degrees of freedom, here we're going to be using Z. Sigma with the tilde is the estimated population standard deviation. You need to have an estimate of the population standard deviation in order to estimate the necessary sample size. And M is the margin of error. Let's look at one example. We want to estimate the mean quiz score with a margin of error of plus or minus 1 point. From the last study, we know that the standard deviation will be around 2 points. Because a confidence level is not specifically given, we're going to assume that it's the most commonly used 95% confidence level. We'll find the multiplier for 95% confidence level, which is 1.960. We're given an estimate of the population standard deviation of 2 points, and we're told that we want to construct a confidence interval with a margin of error of plus or minus 1 point. We can plug these values into our formula now, and it gives us a minimum necessary sample size of 15.366. We always round up, so in this case, I would want a minimum sample size of 16. And finally, we'll conduct a hypothesis test for one sample mean. First, I'll show you how to do this by hand, and then we'll go through the same example in Minitab Express. Here's our formula for our t-test statistic. This is similar to the general form of a test statistic that we've been working with. In the numerator, we have our sample statistic, or sample mean of x bar, minus the null parameter, divided by the standard error. And you can note here that the standard error for the hypothesis test is the same standard error that we saw when we constructed a confidence interval for one sample mean. So for a mean, the standard error is always going to be the standard deviation divided by the square root of n. We're going to be using the same 5-step hypothesis testing procedure. Let's start now by looking at our scenario. A random sample of 35 college students were surveyed and asked how much money they spend at sit-down restaurants each month, including tip. The sample mean was $58, with a standard deviation of $13. Is there evidence that the mean in the population is different from $50? From this scenario, we know that n equals 35. Our sample mean is 58. Sample standard deviation is 13. And the hypothesized population value is 50. First thing we need to do is check our assumptions and write our hypotheses. So to check assumptions, in order to use the t-distribution, either we need to know that the population is normally distributed, or we need to have a sample size of at least 30. We don't know if the population or even if the sample is normally distributed, but the sample size is greater than or equal to 30, so we're going to use a t-distribution. To write hypotheses, our null hypothesis is that the mean equals 50, and our alternative hypothesis is that the mean does not equal 50. Our research question was whether or not there's evidence that the mean is different from 50, so we're not given a specific direction here. This is a two-tailed test. Step 2, calculate the test statistic. Our t-test statistic is equal to the difference between the observed sample mean and the hypothesized population mean divided by the standard error. This gives us a t-test statistic of 3.641. Step 3, determine the p-value. To determine the p-value, we're going to construct a t-distribution, and we're going to find the area that is more extreme than t equals 3.641. This is a two-tailed test, so we're going to have to look at the area to the right of positive 3.641 and to the left of negative 3.641. Before we can construct our t-distribution, we need to compute the degrees of freedom. These are equal to n minus 1, so here the degrees of freedom equals 34. Let's go to Minitab Express now to construct this t-distribution to find the p-value. In Minitab Express, I'm going to construct a distribution plot to display a probability. We have a t-distribution now with 34 degrees of freedom. Our test statistic is a x value, and it's a two-tailed test. Our test statistic was that t equals 3.641. Our p-value is the total area in the tails here. It's going to be a very small p-value. It's 0.000447 times 2, which is approximately equal to 0.00089. Let's go on now to step 4 of the 5-step hypothesis testing procedure. Step 4 is to make a decision. We're going to use that p-value that we just computed to make a decision whether we should reject or fail to reject the null hypothesis. Our p-value is very small. It's less than 0.05, so we reject the null hypothesis. Step 5, we state a real-world conclusion. We're going back to the original scenario to state whether or not we have evidence that the mean is different from 50. We rejected the null hypothesis, so there is evidence that the mean amount of money spent at sit-down restaurants monthly in the population of all college students is different from $50. I'm going to take you to Minitab Express now to show you how steps 2 and 3 could be conducted there. The information that we'll need is that n equals 35, the sample mean equals 58, the sample standard deviation equals 13, the null parameter is 50, and that this is a two-tailed test. Let's go to Minitab Express now to see how that can be done. I'll go to Statistics, One Sample Inference, T, just like we did when we constructed the confidence interval. I have summarized data. The sample size was 35, the mean was 58, and the standard deviation was 13. Now, we will check the box to perform a hypothesis test against the hypothesized mean of 50. Under options, we can confirm that the default alternative hypothesis is two-tailed. Here we have our t-test statistic and a p-value. Minitab Express will round this to 4 decimal places, but it's still the same. P equals 0.0009. So here we have step 2 and step 3 of the 5-step hypothesis testing procedure. You'll still have to do step 1, 4, and 5 on your own though. This concludes the section on one sample mean. If you haven't been doing so between learning objectives, I recommend that you stop now to review the online notes or textbook, or to go into Wiley class and do some of the practice problems or homework problems associated with Chapter 6, Section 2. When we come back, we'll continue with paired means. So far, we've covered one sample proportion and one sample mean. The last section is actually going to be the quickest. It's paired means. And it's quick because it's almost identical to what we just did with one sample mean. The only difference is now we have an added first step of computing paired differences. In terms of whether we should use the z-distribution, t-distribution, or bootstrapping randomization methods, it's the same flowchart, except now, instead of looking at whether the population is normally distributed, what we're really asking is the population of differences normally distributed? And in terms of the population standard deviation, it's the standard deviation of differences in the population. On the right here, we have the formula for a confidence interval for the difference between two paired means. We can compare this to the general form of a confidence interval that we've been working with, and also to the formula for a confidence interval for a single population mean. The only difference between the formula for the difference in means and one mean is that now the x bar and the s have this little subscript d. Otherwise, it's exactly the same thing. The other thing to note is that when we're computing degrees of freedom, n is the number of pairs. For determining the necessary sample size for a confidence interval, it's going to be exactly the same formula, except now instead of being given population standard deviation, it'll be the population standard deviation for the differences. And instead of just margin of error, it'll be margin of error of the differences. It'll be the exact same formula, exact same procedure. For conducting a hypothesis test, we're going to use the same 5-step hypothesis testing procedure. In step 1, when we check assumptions and write hypotheses, we're going to be looking at the distribution of differences. So we'll ask, are the differences normally distributed in the population? Is the standard deviation of the differences in the population known? And again, is the sample size, which in this case is the number of pairs, at least 30? These are the hypotheses that you can write. I believe you saw these earlier in the course. They're essentially the same as when we're working with one sample mean, except now we're looking at the mean difference. So often you'll see this little subscript d being used. Step 2, calculating the test statistic. On the left, we have the test statistic for paired means. These are also known as dependent means. On the right, we have the formula that you saw earlier for single sample mean. Note that the formulas again are almost identical. The only difference is that when we're working with paired means, we have the subscript d with the x bar and the s. Let's look at one example. Data were collected from a representative sample of 30 kindergarten students. They completed a recall task before and after taking a nap. On average, the children's recall scores were 4.2 before the nap and 6.2 after the nap. The standard deviation of the change in recall score was 2.8. Is there evidence that in the population of all kindergarten students, recall scores would increase from before to after a nap? From this scenario, we're given that n equals 30. We can compute x bar d. This is the change in means. In this case, we're looking at before and after the nap. In order to keep this positive, I usually like to do the higher number minus the lower number, but we need to take that into account when we go to write the hypotheses and compute everything else. So in this particular case, I'm doing after minus before. This gives us a mean change of 2, and we're given that the standard deviation of the changes is 2.8. Step 1, check assumptions and write hypotheses. The normality of the difference is unknown, but we have a sample size of 30, which means that we can use a t-distribution. In writing our hypotheses, the null hypothesis is going to be that there's no change. So mu sub d equals 0. The alternative hypothesis is that mu sub d is greater than 0 because we want to know if scores increase from before to after. And note earlier when we computed x bar, I did after minus before. So if there's an increase in scores, then after minus before will be greater than 0. Step 2, calculate the test statistic. We'll use the formula above. Our t-test statistic is 3.912. Step 3, determine the p-value. The p-value is going to be the area in the t-distribution that is more extreme than 3.912 in the direction of the alternative hypothesis. Looking back at our alternative hypothesis, we can see that this is going to be a right-tailed test. So we're going to construct a t-distribution with n minus 1 degrees of freedom, so 29 degrees of freedom, to find the area to the right of 3.912. I'm going to construct a probability distribution plot to display the probability. This is a t-distribution with 29 degrees of freedom, and our test statistic is 3.912, and we have a right-tailed test. Our p-value is 0.0002539. We can use this now as we move on to step 4. Step 4 is to make a decision. We use our p-value to determine whether we should reject or fail to reject the null hypothesis. Our p-value is very small. It's less than 0.05, so we reject the null hypothesis. Step 5, state a real-world conclusion. There is evidence that in the population of all kindergarten students, the mean recall score increases from before to after a nap. Now, I want to go back to Minitab Express to show you how this whole test could be done there. The information that we'll need is that n equals 30, the mean change, or x bar d, was 2, and the standard deviation of the change was 2.8. We'll also need to tell Minitab Express that this is a right-tailed test. Minitab Express considers paired tests to be two-sample tests. So under two-sample inference, we'll select paired t. We have summarized data. Our sample size was n equals 30. The mean change was 2, and the standard deviation of the change was 2.8. Under options, we need to change the alternative hypothesis because we had a right-tailed test. Here's our output. We have a t-test statistic of 3.91, which is exactly what we got when we did this by hand, and again a p-value of 0.0003. One more thing I want to show you here is how we could also enter this into Minitab Express as a one-sample mean test and get the same answer. So if we go to statistics, one-sample inference t, we can again enter our sample size of 30, mean change of 2, standard deviation of the change. We will have to tell Minitab Express that the hypothesized mean is 0 and change this to a right-tailed test, but we should get the exact same t-test statistic and p-value if we run it this way, because a paired t-test is really just a one-sample t-test on the differences. Let's go back to our PowerPoint slides. We have covered all 4 learning objectives for one sample proportion, one sample mean, and paired means this week. I know it seems like a lot, but what I want you to focus on are the similarities between these 3 different types of tests. This is in your online notes, but here we can compare the standard error, confidence interval, and test statistic formulas for all 3. There are some differences between the proportion and the means in terms of computing standard error, but note that the last 2, the one mean and the paired means, are almost identical in both the standard error and the confidence interval and test statistic formulas. The only difference between the 2 is that the paired means have that subscript D to denote that we're working with differences. All of these follow the same general form for a confidence interval and the same general form for a test statistic. So I recommend trying to look at these all together to see the similarities instead of getting overwhelmed looking at all of the differences. This concludes the full video lecture on inference for one sample. As always, if you have any questions after watching this video, or as you're working through the Wiley Plus homework questions or the lab assignments, I strongly encourage you to post those questions to the discussion board on Canvas.